So you got like distribute. He's got control.
Yeah, but still like so we have an island resolution system. Which is super cutting edge, pretty early industry. We finally got rid of our year or so ago.
So you would never do.
Mostly C sharp.
Yeah.
So let's say you have a problem.
That's a good one. That's
Do something.
Such a simple way to understand.
And so you aggregate changes from.
Yeah,
well, there's actually a whole variety of these.
So, other load of libraries.
Yeah. Yeah, I think we need to like set up a recurring event.
So, you know, people create some libraries.
Right, it's like we have a recurring observation for the room, but why is that? I don't know.
Standing libraries. Incredibly small, but.
You give them your credit card and they charge you an exponentially increasing amount of money if you don't achieve your goals.
Yeah. Talking about PayPal?
No, be mine. All right.
Okay, I'm ready. Whenever everyone else is ready.
Yeah, I like it. I think let's do it.
Okay. Hi, everyone. I'm Levi Pearson. I work for Harman International. I'm an embedded software engineer and I also do networking and protocol development. And I'm here to talk to you tonight about CRDTs, which are very cool. And let's get started. By the way, if anybody has any questions, feel free to stop and ask them. I have read a lot on these in the last 2 weeks, and I am familiar with more stuff than I know from the slides. So feel free to ask questions, and hopefully I'll know the answer or where you can find it if I don't. So the goal here is to understand what makes something a CRDT, what the theoretical impact of the idea of the CRDT is, what they're good for practically, and some of the existing CRDTs that have been developed. And most of this comes from a single paper, something a paper as much as it is a gigantic research report. It's like 50-something pages. It's called a comprehensive study of convergent and commutative replicated data types. And there are 4 authors there. And if you study this topic at all, you'll find their names repeated all over the place. They're from 3 different universities, and Zawirsky has recently graduated as a PhD student. His thesis is actually on CRDTs and practical implementation details, as well as some interesting theoretical stuff about how you can minimize the metadata overhead involved in CRDT. And sometimes get pretty big if you do it in a naive way. So definitely check out his PhD thesis if you are interested in CRDTs. Shapiro comes up a lot. He is in France at some university of belong to INRIA or associated with INRIA. I'm not sure exactly how that works there. Some sort of French national institute thing. And then the other two are from two different universities in Portugal. And they also have interesting distributed systems research going on. So if you look up their names, you can find lots of interesting information on CRDTs, vector clocks, and other associated things. Anyway, we're going to go over the basic concept of CRDTs. We'll go over the detailed theoretical model of what a CRDT is and what the guarantees that it gives you are. We'll go over some CRDT specifications. And if there's time, I will talk briefly about garbage collection issues. And I don't actually have slides on the shopping cart example because we won't get there. So the authors of this paper were interested in eventual consistency because it has wonderful properties for scalability. The only problem is that eventual consistency has not had a thorough theoretical treatment. So there are some issues with some previous attempts at achieving eventual consistency in a way that is friendly to application development. So they wanted to improve the theoretical grounding of eventual consistency and also wanted to weaken some of the coordination requirements that previous attempts had had. Sometimes they would require some sort of background consensus algorithm to be running, or require some group membership knowledge, that sort of thing. And sometimes those are still required, but in some situations you can get away with even weaker requirements of your network. And we'll see exactly how you can know what conditions you need out of your network to get the CRDT. So a quick outline of what eventual consistency is. The idea is you have a bunch of replicas of data. Updates to the data are executed at all replicas. And first they're executed at one, then they're sent to all the others. Eventually, all of the replicas see all of the updates that have happened. They apply those updates asynchronously and possibly in different orders from each other. Sometimes concurrent updates of data require some sort of, they conflict, and so they need an arbitration mechanism to decide who wins in the conflict. So one of the major contributions of this paper, and there was sort of a shorter version that was more like 15 pages. One of the contributions of it was this idea of strong eventual consistency. And it provides a formalized model of what it means to be eventually consistent. It does not require a conflict resolution stage. And this is a property called conflict freedom. So before this, CRDTs were called commutative for convergent replicated data types. Now the catch-all term for them is conflict-free replicated data types. So they're extremely scalable and fault-tolerant, and their properties are based on mathematics, and they are reasonably easy to prove if you base them on these models that we're talking about. So there's two ways to build a CRDT. There's what we call convergent replicated data types. They are state-based, and they have weak network requirements, which means you don't have to have a fancy network layer to give you the properties that you need. They are based on the mathematical principle of monotonic joined semilattices. Who's familiar with semilattices? Not too many of you. you should get familiar with them because they come up all over the place in computer science literature and mathematical literature and stuff in general. They will be very useful for reading papers. The other formulation is commutative replicated data types. And rather than being based on state and moving states around, they're based on operations on the state. One of the distinctions between them is that these require some reliable broadcast mechanism of your network layer that has to guarantee some sort of delivery order. And the delivery order necessary to meet the CRDT requirements depends on the data structure. So it will vary from CRDT to CRDT. And the mathematical principle here is the commutativity of concurrent operations. Basically, it says that the commutative property, if you remember from your algebra class, means that you can switch the order of the arguments of the binary operator. It still comes to the same result.
Wait. Sorry, quick question. What does concurrence mean in this context? Because that sort of implies synchronized clocks.
Right.
But I guess that's not something you
that's part of the delivery order mechanism there. The idea is that you get a delivery order, but it doesn't necessarily give you a strong order over all of the operations. There could be some that end up happening at the same time. That it's more of a partial order, or parts of it don't fit in the order, and so it's sort of a happens before relation, and you can end up with a bunch of things that all end up happening at the same time. And I will get more into that later in the formal model of that this work is based on. Anyway, one of the interesting results is that you can always simulate one of these kinds of CRDTs with the other one. In the paper, they present the whole sketch of the algorithm required for sort of the naive way of interpreting one and the other, which is nice for proof, but can be expensive if you try and implement it that way. So it usually turns out that one of them tends to be more suited for your problem than the other. So now I'm going to get into the model for CRDTs that is basically how they formalize this, and these are really important for distributed systems research because there's a lot of results that are impossibility results or things that are possible within a certain set of circumstances. It's very important to know the model that they base their results on so that you know how you have to arrange your system for those results to be useful to. Sometimes it requires that you have something more than just a raw method. You've got to have some protocol beneath what they presented. Anyway, a distributed system is a system that has processes interconnected by an asynchronous network. Sometimes distributed systems are defined in synchronous networks, but in this context, they're asynchronous. Networks can partition and then recover again. Nodes can operate disconnected from the network for some time. Processes can crash and then recover, but when they do recover, they keep their memory. So they have persistent storage. And there's an assumption of non-Byzantine behavior.
Can I ask you about that?
Yeah.
In your research, did you see anybody even attempting to account for any kind of Byzantine faults?
Yes, there are some areas of research that are interested in handling Byzantine faults. What do you mean? Barbara Liskov has, with colleagues, published some recent research She was involved in some early consensus database work and she's continued in the distributed systems research. And her recent work is related to Byzantine faults.
With CRDTs.
Not with CRDTs, just distributed systems in general.
Oh, okay, no, but I'm asking a question with CRDTs. Is anybody, this is a hard assumption then.
Just for background, in case anyone's unfamiliar with the word Byzantine. Byzantine means that nodes may be malicious. So typically, distributed systems are programmed around the fail-stop model. If there's a failure, it just stops and drops off the network. In the Byzantine model, failure may be that nodes start lying or behaving in the worst possible way. So,
yeah, it's possible that you could build on it. Generally, you're not going to
But
be
you
able to
haven't
solve.
seen anybody doing that.
No, you're not going to be able to solve that because that's even harder than consensus outside of the Byzantine fault assumption. So yeah, CRDTs are for the realm where you are moving away from those strong guarantees. You're playing a little bit more fast.
Well, I was just wondering because in cryptography you have this idea of homomorphic commits, which allows you to make statements that are commutative operations that would work in a Byzantine environment. And so there seems to be a lot of similarities, and I just wonder if you'd seen anybody make that connection.
I haven't, but I have seen other people kind of in the same area starting to make connections with these. And it might be possible that somebody is looking into it, and I just haven't seen the publications yet.
interesting. That's an interesting thought.
Okay, so the next we're going to talk about a data model. These processes that are running, they can store atoms and objects. Atoms are base immutable data, things that are comparable directly by value. Objects are, and atoms are immutable. So it's, you have an integer, your integer isn't going to change. You're not going to change some bits in the middle of an integer. Anyway, the idea of an atom is it's an indivisible, immutable piece of data compared by value. Then you have objects, which are mutable, replicated data, and they are collections of other objects and atoms. Objects with the same identity but different location, replicas, and objects are independent of one another. So there's no concept in here in this model of transactions. Something that is an open topic of research in the realm of CRDTs, but it's not covered. So along with data, we have operations on those data. There are clients that query and modify objects via operations. Clients act on one replica, which we call the source replica. The operation executes locally at the source and then remotely. And in the operation model, there's generally two phases to how the operations occur. The first one is the client calls the operation at the source. Some processing may occur sometimes. Phase two is that the update is transmitted asynchronously to all the downstream replicas. Downstream is what we call everybody else. So when we do state-based replication, updates happen entirely at the source replica via an update operation. Then that modified payload is transmitted downstream. And then when receivers get that payload, they perform a merge operation to update their own payloads. And those replicas can be compared to one another via a compare operation. And the operations can also be guarded by source preconditions. And these can be invariants that need to be maintained in order to keep the whole algorithm sensible. Okay, so here we have a causal history model. So for basically what all this math stuff is that the C of x sub I is a set, and it starts as the empty set. And the idea of this set is it's going to collect all the operations that have happened so far. And we call that set the causal history. So when there's an update that we call F, the causal history of the replica modified by F is the union of the causal history with the set containing F. So you just take the set of the things that have happened to it before and you union it with F. You add F into it. So after that, when that set of operations goes to the other replicas downstream, we union those sets together to get the causal history of the resulting update downstream. And so we get a happens before relation where F happens before G, such that F happens before G means that the state corresponding to F is a subset of the causal history of F is a subset of the causal history of G. So that more stuff happened after F in G. Does that make sense? Please ask questions if it doesn't make sense.
I have a couple quick questions that I want to clarify. This model is not in place in any product.
Well, this is a logical model for reasoning about it. It's not necessarily anything to do with the actual implementation.
Right.
So this is a tool for reasoning about CRDTs, and you're not going to necessarily carry around a set of things that you're setting around. Okay, so we make some assumptions about the network, which is that states transmit between replicas at unspecified times, but those transmissions occur infinitely often. And that communication forms a connected graph amongst them. Basically, this means that if something gets corrupted or falls on the floor, it will be resent. This provides you with just a fancy way of saying that messages eventually get everywhere. They may be out of order, and it may take a while, but they do eventually get there. So when we're doing operation-based replication, you have those two phases again. The first one updates the local source replica. You first check the precondition guard. If that's true, you execute immediately and atomically. And then there may be results that are returned to the agent, whatever the term was, performing the operation. But there's no side effects as a result of phase one. And then phase two, if there is a phase two, for a query operation, there may just be a phase one. In phase two, the update executes asynchronously on downstream replicas. So when the operation gets to the downstream replica, the precondition downstream must be true. And that's where the network ordering requirements come in. You can't return any results because it's already left where you performed the operation. It updates the downstream state. And if there are any arguments required, they're prepared by phase one. And again, it executes atomically with respect to all the other operations that occur.
So a quick question. You said no side effects on the source side.
Right.
Doesn't that set grow as well? And so it doesn't grow. That's basically what we're saying.
Well, mean by no side effects there? I think phase 2 also executes on the source node, as well as all the downstreams. So the first part, phase 1, doesn't have any side effects, because all of the side effects that occur have to occur everywhere. And so it takes place locally, but it is part of phase 2.
It's almost like a sort of a commit style
Yeah, yeah. It's
wrap up.
yes, it's a 2-phase process.
Gotcha.
Phase 1, you set things up. 2, you send it out everywhere and apply it locally.
So we talk about state-based CRDTs and operation-based CRDTs, state-based replication, operation-based replication. But we're not going to blend these things together. State-based CRDTs implies state-based replication only.
Yes. Okay. Right. So you can simulate one with the other, and that means any of the CRDs you can build either way, theoretically. There may be one that's more efficient, more easy to express the properties you want, and so that can guide which one you end up using.
So for example, React does operation-based replication, right?
Right.
So they're using CRDT, or at least they implemented an operation-based. And I guess Couch does a little bit, but they're kind of not rigorous.
Yeah, React, Micklejohn, I forget his first name, he is actually working with some of these guys in the research. And so React is definitely fully behind the CRDT idea, and they are doing research in this space. Okay, so we have a causal history model that's similar to the other one. The main difference is that we have an idea of causal delivery. It means that if F happens before G, then F is delivered before G is. And sometimes, in order to make these work, you have to have a delivery model that will guarantee that. Sometimes that's not required. It depends on the CRDT. Okay. So the network assumptions here, the big one is that you've got to have a reliable broadcast mechanism. And so there's a lot of research on various different ways to do reliable broadcast. You can do it with your distributed hash tables, with the various kinds of overlay networks, and there's gossip-based protocols, and there's I think of the term epidemic-based protocols. Lots of different ways, and some of them are more applicable in different environments. Like, if you have a fairly stable server environment in a data center, you might choose a different reliable broadcast mechanism than you would if you had a widely distributed with a bunch of unstable edge nodes.
But it has to be a full spanning tree. It has to.
Yes. Although nodes can drop off and come back, and depending on the requirements you have, that may cause them to take a while to get their updates. But okay, so now we get to the definition of what it means to converge. So if two replicas, x sub I and j of x, they converge eventually if they have these two properties of safety and liveness. Basically, safety means that for all I and j, the causal history of x, when the causal history of x has the same members as the causal history of x of I has the same as x of j, that means that the payloads of I and j are equivalent. And liveness means that if the operation f is a member of the causal history at node I, eventually it will also be in the causal history of node J. Does that make sense? Okay, so what it means for states to be equivalent is when all query operations that you perform return the same values. So there may be a different representation between them, but they will be observably equivalent.
And does this apply to both types of CRDTs?
Yes.
Okay.
Okay, so now we're going to get to the detailed description of exactly what these CRDTs are. So again, CV RDTs are based on the concept of a joined semilattice. And what a semilattice is, so you have a set of values, say a set of integers, or just a set of some fixed values that you care about. Then you have to have a partial order relation, which is a binary operation that applies to all of the elements pairwise of these sets. And it has to hold for everything in the set. And basically orders them. So there's two different symbols that we sometimes see used for a partial order relation. Sometimes you use less than or equal. And sometimes you see that funny box-shaped one on the side. They both mean the same thing. They're an order or a partial order.
So I guess this is where concurrency then comes in when two elements don't have the ordering relationships that they are considered concurrent, right?
Right. In the sense of the state-based convergence, it means that you've got things that are equivalent and you can merge them together if one's not ordered before the other. So a total order means you have something like just less than. So you can't have something that is less than another element, and they work the other way around. So one or the other. Whereas in a partial order, you can have a group of things that are all at the same level in terms of the ordering. So they're all, you can swap them around in the ordering relation, and it remains true. But only for those sets. Yeah.
So does this ordering have to do with time? Is that
It
Causality.
It
What
depends.
happened before, or-
It can be whatever you want it to be, as long as it meets the properties of a semilattice. And that's the confusing thing. A lot of these algebraic topics, they're very abstract. And once you prove something based on the properties of the algebraic stuff, it holds for anything that meets those requirements. And so it doesn't have to be the ordering that somebody else thought of. But it's not always easy to find an ordering and this operation that I'm talking about in the set that apply and work correctly for all the members of the set. So it's actually a relatively hard problem to get your data model set up correctly for this to work right. But when you can get it set up that way, this is really powerful because it's got very little requirement upon the network. So you don't have to have one of these fancy guaranteed broadcast things sitting underneath it. But anyway, so we've got values and partial order relation on them. And then the thing that makes it a semilattice is that you have a least upper bound operation. So who knows what an upper bound is? I guarantee you've all heard of it before. So it turns out that if you think of big O notation, you want to find the least upper bound of the complexity classes that characterizes the one you're trying to to measure, or to characterize. So an upper bound is anything in the set that is higher than it. Okay, so if you have a least upper bound, it's a binary operation on two values. So you want to find an upper bound, and that can be anything that's greater than both of them. So any of those that are greater qualify as an upper bound. Just like if you have a linear algorithm, an exponential algorithm forms an upper bound for it, but it's not the least upper bound. So the idea of the least upper bound is it's the one that's closest to them. So the least upper bound sometimes has that square coupling operation. It's also called join or supremum or a couple other things. So it's kind of confusing. But it's used everywhere, and that's why there's so many different terms for it. Anyway, so if we say that m equals x cup y, that m is a least upper bound under the ordering operation less than or equals if and only if these conditions hold. That is, x is less than or equal to m, y is less than or equal to m, and there's no m prime that is less than or equal to m, where x is less than or equal to m prime, and y is less than or equal to m prime. Basically, there's nothing between them.
I think I'm re-asking the same question, but in practical implementation, we're given time.
Not necessarily. With these, definitely not. With operational-based things, you start to deal with time. One of the advantages of state-based replication is that time is not a factor.
So I would be comparing.
Whenever you do an update with the convergent replicated data type, you're sending the entire object, the entire payload that you're tracking, or some chunk of it.
And I have some comparison that I'm able to do on these
Right.
payloads. And practically speaking, that would be, like in a real world implementation, what might that actually
Well,
be?
so one example would be if you're trying to maintain some sort of highest value seen so far kind of object. And this would use the set of integers as your set. And you use the standard numeric comparison as your ordering. And then for the least upper bound operation, you use max. So the max function provides the least upper bound. There's no notion of time here. It's just that because that least upper bound exists, you can always merge all these things together and you end up at the same state. Anyway, so it's kind of tricky to understand what this means and set your data model up this way. But if you can do it, then you get wonderful properties out of it. And we'll see some examples of it. Anyway, the other important point is the last one there, because, well, actually the last two of them. The merge operation of two states is the least upper bound operation. And then when you do an update locally, all of those operations have to be non-decreasing with respect to the ordering. Either it has to be at the same order or higher after the operation. This sometimes you have an ordering with respect to the amount of information you have. And for it to be non-decreasing in this way, it means you have to increase the amount of information. You can't ever decrease it. Does that make sense?
Not quite yet.
Like you can say that there's the set of integers, and then you're working with subsets of the set of integers. That means any of your operations can make your subset stay the same or can grow it, but you can't shrink it. And then the least upper bound would be the union of two of those subsets. Does that make sense? That's like that.
Don't hinge on me.
All right. It took me a long time to get to the meager level of understanding of this that I had. So if it's going over your head, don't worry about it.
So in the case of the max example you just gave, order doesn't matter, right? So that's
What's that?
in the case of the max example you gave, order doesn't matter. So it's still important. This last point is still important.
It does matter because we're not talking about order with respect to time. We're talking about order with respect to least greatest. So you can't have an operation that decreases it because that will disappear when it gets merged. That makes sense. Yes, you can. Min is another valid implementation as long as you initialize it like infinity. Okay. So hopefully that makes some bit of sense. If not, go look at it later. If you study the idea enough, it will eventually make sense, I promise. Okay. And this is basically the example I just talked about. We have an integer counter. It's not a counter in the normal sense. Counting the number of them, the max counter. So it tracks the maximum value ever seen. So our ordering is just standard numeric ordering. We merge with the max operation. Payload is initialized to 0. We have a value operation that just returns the integer that we've stored. And then we have a comparison that says x is less than or equal to the other x. Increments the state. So if you perform an increment at a replica, and it's currently say 3, it will become 4, and then send 4 out to everybody. And so everybody that gets that will have their internal state, and then they'll just merge the two together and with the max operation. So everybody will eventually end up with the highest value that was ever seen anywhere. Does everybody believe that?
But this doesn't provide a way of creating unique counter values.
Right. You can't see any of the intermediate states.
Two people might get the same value if you're using this as a counter. Because
right. You use it as a counter,
right.
as you know, the number of hits or the number of
yes, right. This is a more abstract counter.
Yeah. This is like keeping track of some sort of statistics, like the maximum load seen anywhere today.
A high water mark.
Yeah. So, I mean, this is just a small example. There are many more that are about this size. So this is about what it takes to specify the smallest CRDTs. Okay, so now we have commutative replicated data types, and these are based on operations. And it requires a reliable broadcast strong enough to guarantee some delivery order. So the particular delivery order operation or the ordering relation is specified per data type. Some operations are not ordered. Those ones are concurrent. And so in the notation we show up as parallel lines. So for F to be concurrent with G means that F is not ordered before G and G is not ordered before F. So we know that all replicas converge to the same state when all of the concurrent operations commute with one another, which means that all of the execution orders are consistent with the delivery order, because the ones that are not in that order They can be rearranged however you like, and it doesn't change the result. So reliable causal delivery is a kind of delivery order. It doesn't require agreement. It's immune to partitioning in the sense that all of the connected subsets are still working when there's a partition. And then eventually when the partitions are healed, the deliveries all occur on all the nodes. Some of them may need to queue up a bit in order to satisfy the delivery order requirements. And so the delivery order requirement for commutative replicated data types is never going to be stricter than this causal delivery model. Sometimes it's weaker than that, depending on the data type. And some of them that we'll look at don't have much of a delivery order at all, because all of the operations commute. But that's kind of a worst case, is you may need causal delivery. Okay, so the relationship between the two, state-based convergent replicated data types, they're relatively easy to reason about once you grasp the concepts of lattices and least upper bounds. They require only weak network properties, and then you don't have to track the members that are communicating. It may be inefficient for large objects because updates require sending the whole object. And this basic kind of algorithm has been used in a lot of distributed file system type things. So operation-based commutative replicated data types, they're harder to reason about because it requires reasoning about the causal history and maintaining that ordering. But they can have greater expressive power. And you don't have to get your mind around semi-lattices. Of course, they require an underlying reliable broadcast protocol, and those generally require membership tracking. On the other hand, if you already have those in place, sometimes they provide extra mechanisms that you can use to help out with your application. We get to talking about garbage collection. Sometimes they've got some stuff that helps you out knowing when it's safe to collect garbage.
State-based CRDTs are using 5 things that I know well. Operation-based are using 4 things I've never heard of.
I've heard of Bayou before, but I just heard of it. I don't know what it is.
Was there any example you came across?
Bayou was made for Palm Pilot syncing. It was a distributed system for syncing calendars with Palm Pilots.
Is that what took down Palm?
But I mean, I don't know if that gives any context for.
Well,
maybe, yeah.
Was there anything
Well,
you came
I
across that
think-
was a well-known example?
No, and I think that's because reliable broadcast protocols have not been around that long. So, I mean, because you have weaker network requirements, and we've had TCP/IP for a long time, and that's good enough to give you the sort of network properties you need for the convergent replicated data types. And so there's a lot more historical examples of that sort of thing.
Was there anyone that was really optimistic and plus the evidence that people would like to pursue Operation CRDT technology is there to support that?
I think that there's definitely, at least in this group, they've developed a whole bunch of their more advanced data types end up operation-based because it's easier to reason about some things when you've got some of the delivery order stuff managed for you. So I think we'll see more operation-based CRDTs now.
So this isn't really distributed example.
operation-based with similar to like MySQL replication, where it's specific queries going through in order that get replicated to each slave, which causes a whole different set of problems.
Yeah, I mean, if you don't have the reliability guarantees that, and it can slow you down if you're requiring the strict ordering and you don't have any operations that'll commute. You're basically stuck with requiring some sort of consensus step along the way all the time. So, yeah, I think that's why you don't see a lot of those, is because the theory behind them was developed more recently, and the substrate that you need to make them work has only recently really come into the mainstream.
I think it might be interesting is to note things like form
Right.
has similar goals to a CRDT, but they didn't have these strong theoretical guarantees for it. So many operational transforms which are used for don't.
Actually, a lot of the early papers by these authors are using CRDTs in the same space as the operational transform stuff. Yeah, they developed the tree dock protocol. There's something called logboot, something like that anyway. That they're based on CRDTs, and they were sort of answers to the operational transform work. So yeah, you're absolutely right that they're definitely in the same space. Okay. So now we look at some CRDTs. So in the paper, there are these categories of CRDTs that they present. There's counters, which we've looked at, but not just a max counter. There's actually things useful for counting things. You know how many rather than just the maximum value. You have registers, which are storage areas that you can set and clear and set again later. They have basically the same semantics as registers in a computer. You can create sets, although it turns out to be a little bit tricky to get properties of sets that you want. And there's different versions of sets that end up with different properties depending on what kind of operations you need to support. They have some algorithms for graphs that I'm not going to get to. And they also talk about, they list two different algorithms for doing cooperative text editing. So I encourage you all to download the paper and look through these operations, and it's a great resource for if you want to use these things practically, because they have these recipes spelled out along with the caveats that come with them. So very handy stuff. So all of the algorithms are presented with this basic outline. This first one is for state-based ones. We've got a definition of what the payload is, and it includes the initial value that you started at. And then we have various operations below that. There's always a query, so you can find out what the current state is. There's sometimes a precondition that has to be in place before the query is possible. Anytime there you see a let, that means it is an atomic, non-mutable operation that's occurring. It's an expression that has no side effects. And then you'll see some update operations. They sometimes have preconditions. They'll sometimes have a let part and then some side effect part. There's the comparison that always exists. This is the ordering of your semi-lattice, basically. And then you have the merge operation, which is the least upper bound of the semi-lattice of the payload. That notation makes sense to me. Okay. So for operation-based CRDTs, again, we've got the payload and query, which are basically the same. Then we have the update operations, and we have the at source segment, and then we have the downstream segment. The preconditions are optional, depending on the needs of the CRDT. And then you'll see at the source, there's no side effects for the at source part. And then for downstream, there's a precondition that has to be guaranteed by the ordering. If it's some of the other preconditions, it's like something your application will have to worry about. But for this downstream one, if you're not guaranteeing that precondition, then your CRDT is broken. If that makes sense. So downstream, we're doing the asynchronous side effects to the state. Okay, so here is an operation-based counter that is presented in that style. We've got a payload that's type integer, and we call it I, initialized to 0. We have a query called value, and it returns an integer j, and we calculate j by just setting it equal to I. We have two operations that update. They are increment and decrement, and we don't need to do any upstream calculation in this case. We just downstream set I equals to I plus 1 for increment, and downstream set I equals to I minus 1. And because addition is commutative, you can reorder all the operations and you have the same result. That one's nice and easy. Now we have one called a G counter, because there's a global invariant trying to track. So now instead of, this is how you create a counter with a state-based replication system. Before we had just a single value, but the problem we ran into is that anytime anybody incremented, you just got the max of anything ever seen. You weren't incrementing, you can keep all of the individual increments that happen in each location. This allows us to keep all the increments and sum them together in the end. But we're doing it state-based rather than operation-based. Okay, so our payload now, instead of being a single integer, is now a vector of integers, one for each of the reference. And we call that vector P, initialized for all of the members of 0. Then increment update. And here, each node knows how to get its own ID, which is going to be an index into the vector that it will use when it increments. So it gets its own ID, and then it indexes into the vector and sets and increments that value by 1. Our value query is just going to sum the entire vector. And then we have the comparison operation. It says for all I for each index in our vector that is in the range vector x dot p I is ordered before y dot p dot I. Basically, it means that none of the values, if none of the values are greater than in the other one, then it's ordered less than or equal to it. And then merge just takes the element-wise maximum. So there you go. We have a state-based counter. And this is how you create a state-based counter that can decrement as well as increment. Because we have the requirement that we can never go backwards, we have to have some other way of tracking decrements. And so we keep a second vector that sums all the decrements. And then when we query the value, we sum the positive ones, we sum the negative ones, and then we subtract the negative ones from the positive ones. And that gives us our total value. And you see that the comparison and the merge are just the same as the previous, you're just doing it twice. Once for each set, or once for each vector. Is everyone clear on how that works? Okay, now we have, now we're getting into the registers. This is the last writer wins register. So this is another convergent data type, state-based, because it's got the compare and merge operations. So we're going to start with a payload of any type X. We'll call the value X as well. And we start with a timestamp T. This is going to be something like a logical timestamp, actual time. Basically, assignment creates, it sets the value, which starts out undefined. We've never seen that upside down T thing before. That's again from this order theory. It's the least element in Lattice. And it's typically used for the information ordering of things, programming language semantics, to a value that doesn't have any information. So, okay, so when we assign, we set the value to into X, and we put the current timestamp into the timestamp. That gets propagated out. Value just returns the current value. Compare is an ordering on the timestamps. So this is a case where we're using the time order in a state-based algorithm. And then merging basically says that the one with the latest timestamp is the one that stays. So any node along the way can miss an intermediate state, but they're all going to end up eventually at the same state.
How is the now determined?
That's something that you have to supply via, Lamport clocks or vector clocks or any of those kind of logical causality clocks in the literature. Okay. Any other questions on the state-based last writer wins? We have an operation-based one, which looks almost exactly the same, except instead of sending a state around, we send around the assignment operation. And in this case, it only takes effect if the timestamp is after the one that's already there. So this is an interesting case, and the two of them are based on the same basic principle. Yeah.
So here you have to guarantee that I'm going to see the same timestamp. Two different operations.
Yeah, and that's part of what the lambda clocks or the vector clocks give you. Yeah, if you were to just use your native timer or whatever, then you're going to run into problems because it's not synchronized. Okay, so another option, aside from the latest writer-wins option, in the case where you don't want to lose intermediate states if there's a conflict, is to have a multiple value register. And in this case, what you do, it's again a state-based operation. So if you merge two conflicting states, rather than saying it's either one or the other, you end up with a merged state that contains both of those values somehow. And it's up to you as the user to define what it means for it to be both values at the same time. But generally, a user is going to have to say, oh, I meant it to be that one, and apply an update or an assign operation to fix it at one or the other. And I don't worry too much about the crazy math stuff there. It's basically using a version vector to keep track of all of the different, each time a node updates it, they will increment their index in the version vector. So you can keep track of what everybody has said about the state. And an individual node can make an update to what they did, and that will overwrite the previous one. But if they're different, if the version vectors are basically ordered the same, then you merge them together into a union of the states. I think that's what it's saying. The basic idea is the version vector in there, which is a really cool idea. But I don't have a lot of time to get into. So these are the rest of the operations that go with it. Yeah, you can see in the merge operation there, we're taking the union of A and B, which are both sets of values with the version vectors. And for each one, we're taking the key and vector pairs that exist in B, and either version vectors are concurrent or V is ordered before W, or the opposite for the other one. So this is basically pulling in some of the properties of causal ordering into convergent state-based data type. So this is one of those things that's actually kind of a hybrid between the two, although we're basing it on the substrate of merging data rather than sending operations. So now we get to sets. Here we have this, starting at an empty set, we can add an element by unioning our current set with the set containing the element. We can look up the element by determining whether it's an element of our current set. Comparing is just our subset relation. And then merging is a union. So it's pretty straightforward to do a state-based set. Here we have a two-phase set where you can add and remove. And this is where we introduce the idea of a tombstone set that I know we've talked about before here. But in case you're not familiar with a tombstone set, it's like when we were keeping track of decrements. We had to keep track of them in a separate data structure because we can't ever take information away from the primary positive. But this introduces.
Wouldn't this get into trouble if you add, remove, and add the same item again?
Yeah, just about to say that.
Okay, so
Basically, once you remove something, the removals take precedence over the additions. So future additions don't change the state of it. Once you put a tombstone in, it stays dead.
But theoretically, you could add another tombstone for your tombstones, right?
Well, there's other ways around it besides doing that. And then there's the idea of garbage collection, where if you reach a certain point of agreement between your replicas, you can say, okay, we're going to reset our tombstone. We're all up to the current state. We can get rid of those, and now if we want to add things back in, but that's not something that falls into the core of CRDTs. It's sort of a background thing that you can. But that's a general thing that they talk about, is that you can move your operations that need to be highly available into CRDTs, and then a lot of things that need stronger consensus, you can kind of let them build up in the background and perform them when you notice that everybody that needs to be in consensus is available to agree. And so it gets the need for blocking on consensus out of your application's fast path and into the background.
So part of that might be just blocking everything, all your replicas temporarily.
Right, that's sort of the
Some sort of transaction.
yeah, that would be the easy way to do it, but would cause everything to just stop for a little while. On the other hand, you could use some sort of consensus protocol where everybody's sort of voting on whether to do that thing or not. And that keeps you going, although it can slow you down a little bit. So if you wait for a pause, or maybe it's sort of like garbage collection in memory management, you don't pick up after yourself while you go. You wait until there's a big pile, and then you just kind of shut it off. And you wait for an opportune moment to execute those kind of things. Anyway, I think you've got the gist of the two-phase set. And here's another set that's state-based, or I mean operation-based. And this depends on a uniqueness property of the elements that you add. So this is the way around the tombstone problem, is that you can make each item unique by adding a UUID or something onto it. So the next time you try and add it, it's not the same as the previous one, so it can be added again. So you've got the semantic value along with some uniqueness thing you tack onto it. So this one doesn't have that in it, but this is the general idea that you can use to build up a larger data structure that needs that kind of property. Oh yeah, here's the remove operation. So the trick here is that we've got prerequisites or preconditions. E has to be unique, meaning throughout the entire execution. And given that E is unique, then you can remove it later. But you can only remove it if you currently have it in your replica. This precondition runs at the source, so it blocks you from trying to remove something that isn't in your replica. And we have a downstream precondition here as well. It says that the addition of it to the set has to have already been delivered. Because if you don't have that precondition, then there could be an ad waiting to be delivered somewhere in the network. You could deliver your remove, and it's not there yet. And then the ad would apply, and it would lead to an inconsistent state. And so that downstream precondition is a critical one for this kind of set. And again, that's something that you have to guarantee through your reliable broadcast mechanism, guaranteeing a delivery order on messages. And that's all I have prepared, and I'm sure I've gone way over time, but thank you for listening. Do you have any more questions or comments? Okay.
All right. So yeah. So and then just bookkeeping stuff again. So next meeting will be about Bitcoin. I've had actually a few different offers for people to present. So I actually have a list of possible topics. If you were interested in presenting at all, I think Jay so far is. But if anyone else was interested in talking about it, I think we're gonna like just sort of have 2, maybe 3 sort of small sections to discuss, and then we'll talk about some different angles of Bitcoin, like how to use it, its history, how it works,
how to invest.
How to invest, right? How to lose all your money. How to feel a little bit better than Tom. No, I don't know.
Don't want to talk about it.
I don't want to. So yeah, so next time will be Bitcoin. Again, this is just the third Tuesday of the month. So we'll look forward to seeing you then. And yeah, let me know if you have any other questions or want to talk after. But thanks for coming.